for passenger cars, trucks, and other large engines. Reinhard graduated in mechanical engineering and received his PhD from Graz University of Technology. And he's going to talk to us today about the VISION-xEV program. So I will hand over control to Reinhard and mute myself.
Yeah, thank you, Eric, for the introduction. Good morning, everybody, also from my side. It's my pleasure to provide you an overview of the VISION-xEV project, the achievements obtained so far, and an outlook regarding the activities in the remaining time of the project. Let me first provide a few key facts about the project. It's the VISION-xEV has got the full title, Virtual Component and System Integration for Efficient Electrified Vehicle Development. It's one of the GV02 projects, and it was started in January 2019 and will last 36 months until end of 2021. The consortium is composed of 14 partners from 10 different European countries, and the overall budget is close to 4 million euros. And the project coordination is with AVL. The consortium is of a very well-balanced composition and includes partners from the vehicle industry, from the software, hardware, and engineering service providing industry, as well as in total 8 university partners that contribute with their outstanding know-how and expertise. The overall objective of the VISION-xEV project is the elaboration of a generic virtual component development and system integration framework in order to facilitate an efficiency gain of hopefully larger 25% in the development of all kinds of electrified vehicles, ranging from mild hybrids to full hybrids, plug-in hybrids to full battery electric vehicles. The specific technical objectives to meet the overall goal are aimed at a considerable effort reduction for simulation model setup, for their parameterization, for coupling them together by simultaneously largely increasing the model predictive accuracy. The research and innovation activities of VISION-xEV are carried out on the basis or according to the requirements and needs of dedicated development tasks related to 4 use cases defined by the industry partners CRF, Renault, FPT, and AVL. So these use cases are related to battery thermal management optimization, internal combustion engine and after-treatment system matching for a plug-in hybrid passenger car vehicle, heavy-duty hybrid powertrain system architecture analysis, and electrified powertrain thermal and energy management. The detailed objectives and goals of these of the work packages are closely related to these use cases, and these will finally also serve as the basis for the assessment of the target achievement of the VISION-xEV project. The focus of the specific research activities are on the development of scalable 3D and 1D models of the major components and subsystems of electrified powertrains. And these comprise models of battery, e-machine, inverter, also engine and turbocharging and after-treatment system, especially important in the context of hybrid vehicles, including the related methods for their seamless parameterization. The activities are also aimed at the elaboration of interfacing, integration, and co-simulation technologies and the related methods for fast and easy coupling of the models of the different electric components, the thermodynamic components, as well as the electrical, thermal management, driveline, and vehicle models. And finally, the consortium will demonstrate the applicability of the newly developed and updated models and methods to dedicated simulation tasks related to the 4 industrial use cases, and perform an assessment of the impact of the VISION-xEV project with respect to the achieved development efficiency gain. In the following, let me outline the activities and major outcomes achieved so far regarding performance and thermal modeling of the electrical components adopted in hybrid and battery electric vehicles. In the first period, the project activities in the area of electrical energy storage modeling were devoted to elaborating a consistent workflow for integrated battery and supercap performance and thermal simulation. The work of the partner VUB was dedicated to streamlining the experimental battery cell characterization and parameter identification process, and to set up 1D electrothermal cell models as well as detailed 3D battery cell models. Validation of the resulting models has been achieved by comparison of the simulation results for a broad range of charging and discharging characteristics with the corresponding experimental data. The activities of partner CNR were focusing on the experimental characterization and model development for lithium-ion capacitors, again for a wide range of operating conditions in terms of charging and discharging and in terms of temperature range, as relevant for the industrial applications. For this purpose, a test environment was set up at CNR and equipped with the necessary electrical and thermal measurement devices, along with the related testbed software. The cell performance tests and thermal characterization were done for a broad range of pulse charge current characteristics, as well as ambient temperature conditions. The simulation models that were set up based on the experimental data were aimed at fully reflecting in an accurate manner the electrical and thermal cell behavior, and these were finally validated on the basis of the experimental test cases. So in order to enable seamless import of the experimental data as well as the battery and supercapacitor models developed by VUB and CNR, AVL suitably adapted and extended the interfaces of its in-house 1D and 3D simulation tools. With this, hybrid pulse power characterization measurement data can now be directly imported and used for calibration of equivalent circuit and semi-physical cell models to be further used in the different 1D and 3D simulation platforms of AVL. So these platforms now also support the direct import of equivalent circuit model parameters, as well as the import and interfacing with third-party models provided as FMUs, for instance. So in order to fully utilize the the accuracy of the detailed multi-physics 3D modeling in fast 1D system level simulation. A model order reduction methodology was developed as well and validated for application to energy storage devices. With this newly developed methodology, a considerable reduction in model setup and parameterization effort could be achieved when compared to traditional approaches. The emission modeling activities were conducted at the University of Ljubljana and are related to the detailed development and validation of an integrated multi-physics modeling and simulation, different types of e-machines. The chosen methodology for the modeling fully takes into account the electromagnetic, thermal, and fluid flow effects onto the performance and thermal losses of the induction machines and electrically excited, externally excited synchronous machines. The novel approach adopted for the modeling allows also for the thermal connections to be made to the inverter and and also to the gearbox, for instance, which goes considerably beyond the current state of the art. The realistic description of the heat flow between the main components of the e-machines and the neighboring powertrain components the e-machine is embedded in, combined with nonlinear electromagnetic properties of the e-machine, now allows for comprehensive studies to be conducted of e-machine characteristics with a strong emphasis on its thermal behavior, especially in overload operation. High-fidelity multi-physics 3D models of inverters were set up by AVL Thermal and HVAC to investigate the performance and the thermal behavior of these power electronic components under real operating conditions. The 3D inverter model was then used as the basis for the automated generation and parameterization of a 1D thermal model, again based on a suitably developed model order reduction technique. Besides that, a 0D electrical model of inverters has been set up, which includes functions to calculate the transistor losses as well as the ohmic heating losses of the bus bars and the wires. A methodology for coupling of the thermal 1D model and the electrical 0D model was developed as well, enabling now to efficiently perform electrical thermal simulations of all kinds of inverters and other power electronic components adopted in future vehicle powertrains. The validation of these combined 0D and 1D inverter models confirms the accuracy of the simulations, enabling now the calculation of conduction and switching losses by taking into account the performance of the involved semiconductors, and also depending on representing the impact of phase currents, switching frequency, junction temperature, and DC voltage, for instance. In the following, the activities and the major outcomes achieved by Politecnico di Milano, University of Thessaloniki, University of Valencia, and further partners regarding performance and thermal modeling of hybrid powertrain thermodynamic components are presented. In the context of advanced engine modeling, 1D models of the engines adopted by the industry partners in their use cases were set up. And these models include detailed submodels of the corresponding intake and exhaust devices, the turbocharging elements, as well as the corresponding engine coolant and oil circuit models. Model validation was achieved based on reference experimental data provided by the university partners. These models now serve as a basis for the application to investigations of advanced engine technologies in combination with powertrain hybridization. And with these engine technologies comprising, for instance, electric compressor devices, usage of or adoption of Miller and Atkinson cycles, cylinder activation, and others. To capture the transient engine thermal behavior, a model for simulating the movement of the incompressible fluids, so the coolant, water, and the oil, and to predict the heat exchange between the solid structure elements and the coolant and oil fluids was developed, and resulting models were set up and validated for engine operating parameters that were obtained by testing the engine on the test bed for plug-in hybrid electric vehicle use cases and operation under both motoring and firing conditions. The integrated thermal model resulting from these activities is characterized by high accuracy and high simulation performance, and is available as a functional mock-up unit for being linked with the engine models developed by partner Politecnico di Milano and being embedded in vehicle powertrain models provided by the other partners in the next phase of the project. Activities on turbocharger modeling at TU Berlin and KTH were aimed at further advancing the methodology for joint simulation and experimental characterization of turbocharging devices and e-compressors that are becoming increasingly popular in electrified and hybridized vehicle configurations. So for this purpose, both adiabatic and diabatic experimental investigations on special hot gas and e-booster test benches were performed. And these experimental tests and related 3D CFD simulations under real engine pulsating flow conditions were then used to upgrade available models for the turbocharging devices with regards to taking into account the heat transfer inside the turbocharger and the e-booster on the performance. The 3D simulation results also enabled the development of an exergy-based loss estimation method and the generation of advanced thermal models of the engine air path turbocharger system with a largely improved prediction accuracy. Well, compared to conventional non-electrified powertrains, the post-Euro 6 exhaust system in electrified vehicles is expected to be highly complex and potentially involving technologies like electrical heating and phase change materials. In addition, the long zero flow operation of the exhaust system in hybrid applications during pure electric driving and the associated risk of a light out of the exhaust after-treatment system imposes quite tough accuracy requirements regarding the heat loss simulation. So therefore, the after-treatment system component models and methods were suitably extended into these directions, and new models were developed by University of Thessaloniki in close cooperation with Renault to deal with these challenges. The newly developed models were thoroughly tested in order to ensure its validity over a broad range of operating conditions, and also to ensure the connectivity and portability within the simulation model ecosystem developed inside VISION-xEV. So as a result of the component modeling activities in the first 18 months of the project, a comprehensive set of easy to parameterize models with increased predictive accuracy is now available. And furthermore, innovative approaches for seamless model order reduction and parameterization of fast system level models based on high fidelity 3D simulation results were elaborated. In the second phase of the project, we're now focusing on integrating and coupling the different electrical, thermal, and thermodynamic powertrain component models together to build up the generic framework for the virtual analysis and optimization of the different XEV related engineering tasks. So in this context, different coupling strategies ranging from direct model implementation via FMI-based model coupling to multi-rate co-simulation techniques are going to be investigated. At the current state, the overall concept for the flexible modeling of the electrified and hybrid powertrain configurations, supporting different levels of fidelity and complexity, is fully defined, and first coupling tasks have already been successfully realized. Considerable achievements, for instance, have already been obtained for the coupling of the engine and the after-treatment system models, allowing now for application of the coupled simulation models to various analysis tasks, such as prediction of tailpipe emissions for different drive cycles, or the evaluation of the impact of engine start-stop operation on fuel consumption and emissions. And besides, a novel methodology has been developed to speed up the simulations and to achieve CPU to real-time ratios close to 1. Future activities in this area will focus on the assessment of different coupling and co-simulation strategies and to widen the portfolio of the supported models and tools. So due to its importance for the overall energy consumption of hybrid electric and battery electric vehicles, major focus of the research work in the second phase is also on the elaboration of a comprehensive thermal system layout framework. So this framework is intended to also fully support vehicles' thermal management systems and heating, ventilation, and air conditioning system layout and optimization. So a flexible open framework architecture is supposed to allow an easy coupling of the VTMS and HVAC system models with the electrical and thermodynamic powertrain component models of the partners as they have been developed and set up in the first phase of the project. Dedicated project activities are also carried out at UPV, aimed at providing a platform for optimization of electric and hybrid vehicle energy management control related tasks. Preliminary achievements already confirm the applicability of the proposed approach to minimizing fuel consumption for different drive cycles and vehicle configurations by fulfilling, for instance, different battery state of charge constraint. Further work will be devoted to extending the already available features and capability towards additional vehicle electrification and hybridization configurations, as well as further operating modes. In the course of the third project year, the impact of the VISION-xEV virtual component and system integration framework on the achievable development effort and time reduction will be demonstrated and assessed on the basis of the 4 industrial use cases. Demonstration and the impact assessment will be carried out by comparing the development effort associated with traditional development processes with the efficiency gain when applying the VISION-xEV framework to the different use case related engineering tasks. The demonstration and impact assessment will be based on conditions and requirements related to real-world driving cycles. And for this purpose, representative velocity and altitude profiles have been derived on the basis of real driving measurements for a series of tests that were conducted on the different routes in Greece and in Italy, using 3 different plug-in hybrid vehicles. As an outcome of these studies, a series of specific driving cycles, together with the assessment of the impact of different operation parameters on the electrified powertrain energy consumption and emission characteristics, is now available for use during the impact assessment activities of the project. With regards to the plug-in hybrid electric vehicle use case of Renault, the use of different power sources, thermal and electric, results in a complex interplay between the engine and the after-treatment controls. And therefore, the simulation models of the innovative catalytic after-treatment components are going to be set up, and including electrically heated catalyst and phase change materials for the use case. And such innovative exhaust line concepts will be further evaluated on a virtual basis with the experimental data used to validate the model-based development approach. Regarding the FPT use case related to the hybridization of the city bus configuration, component and experimental data have been exchanged with the partners as input to the model setup and parameterization. And the initial version of a co-simulation environment to build the integration simulation framework for the related use case is already under preparation. So in addition, the baseline regarding the current practice, the current development practice, has already been established and will serve as a reference for demonstrating the achievement of the main technological objectives in the final project year. Yeah, with this, I'm now at the end of my overview regarding the content and current status of the VISION-xEV project. And let me take the opportunity to thank you very much for your interest. If you would like to receive further information, please feel free in directly contacting us. And with this, I'm handing back over to Eric. Thank you very much.
Okay, excellent. Thanks. And questions have been coming in. So I will remind the audience, if you have a question, you can send it through the Q&A button. We expect that we probably won't be able to respond to all the questions live, but the panelists can actually respond to them in text in the Q&A thing. So you may get a response in text afterwards. But let me ask a few of these questions. So here's sort of a hard one, but I think it's a really interesting question that Abdullah Pam asks. How do you position or assess the evaluation of this simulation effort, in function of the software used or the modeling approach, or the structural and functional approach, which to me, I guess, asks the general question of, is there a way to evaluate how much this modeling effort contributes to the advancement and efficiency of a vehicle?
Well, that's these are the or this is the focus of the activities in the final project year to work out and to demonstrate the efficiency gain that can be achieved by using the models and the model interfacing and co-simulation approach developed within VISION-xEV. And that's exactly where the industrial use cases come in. So related to each of the use case are dedicated development tasks that are currently carried out in either by simulation or in a combination of simulation and experimental work. And it's now the goal to apply the newly developed models and methods to these engineering tasks, and to demonstrate how the newly developed model parameterization workflows, let's say the seamless working and seamless coupling and co-simulation of the models can contribute to reducing the number of required development iterations by reducing individual development steps, so to finally achieve an overall efficiency gain in the range of 25% and above.
Okay, excellent. And I think let's do one more question, and for the other questions that are coming in, hopefully you can answer some of them in text as we move forward. But there's a question actually asked by two people, which is that you've developed models for subsystems that are detailed and well validated, but do you intend to, or have you already interconnected all of these subsystem models into one simulation? Or do you plan to use them, the output of one model as the input of another, and sort of study them separately? Or is there an integration element to the whole project?
Well, the idea is that to facilitate with by defining and setting up common interfaces and co-simulation methods and techniques, to being able to cope with the heterogeneous model ecosystem of the industry and the supplier industry and academia. And within this consortium, we try to demonstrate, let's say, to update and to set up these interfaces, and to demonstrate the seamless interfacing of various types of models, and to also to demonstrate how it's possible to exchange models among the partners, either as open models, but also as encapsulated models. So in order to keep or to protect IPs of the partners, but still enabling other partners to use these models in the context of a full powertrain or vehicle simulation configuration.
Okay, let's do one more question, because I think this one's a fast one. This is from Edward Reclaru, and his question is, will the models be made public in any way in situations where data might be considered company secrets?
Well, probably not all of the models, but some of them, especially those developed at the academic partners, that could be shared with others, third party after the completion of the project. Probably not as open models, but as functional mock-up units with opened up dedicated interfaces so that I/O data channels can be utilized, and the models can be such used in beyond the VISION-xEV project.
Yeah. Okay. Great. Well, thank you. I know everyone is applauding individually at their individual computers. I'd like to thank Reinhard Tatschl for his presentation, and we will move on to the next